And now I'll introduce each one of these guys separately when they speak, but we have quite a slate here of experts. Stephen Boros is an expert. His company makes large diameter polyethylene pipes. Steve and I have been working together many years. Michael Camera is an expert on the resin. He'll talk to us first. Matt Danish takes that resin, converts it into the XXL pipe. And then, of course, Mike James is one of the most prolific guys that works in the larger diameters in the world, certainly in North America. I love hearing Mike talk about all of his stories. And then our bench, of course, are two of my engineers. And then Natasha Arjujo from Agru is VP of Sales and a big pipe supporter. And then her colleague, Drew, is going to also assist with particularly the larger XXL questions as it relates to HDPE, taking over this big market that is currently dominated by steel and concrete. All right, now with no further ado, Mike Camera, come in and tell us a little bit about yourself and what you do at LyondellBasell, and who is LyondellBasell?
Sure. Hopefully you can hear me okay.
Yeah, you bet.
Perfect. All right. So my name is Michael Camara. Thanks for introducing me, Pete. I am a researcher currently with LyondellBasell. We are one of the largest resin manufacturers globally, supplying polyethylene and polypropylene primarily. On the researcher side, I primarily focus on high density polyethylene with a specialty more around pipe.
Well, this black and I call it the salt and pepper mix, Michael. We get a lot of play, and people are like, they just think it's just like any other polyethylene that they have under their kitchen sink. But Mike, it really isn't, is it?
No, it isn't. So polyethylene pipe is a highly engineered resin. Is not technically a specialty resin, but can honestly be viewed as such. It is highly engineered, very specific for the applications that it's used in.
Yeah, well, you guys do a great job with it. You supported the Alliance and our educational efforts for a long time, you and your colleague, Doug Keller. So we appreciate you for that. All right, take it away. And if I mess up the slides, let me know, Mike.
Of course. All right. So as Pete mentioned, I'll be focusing on the resin side of things. Before we get into some of the, special characteristics of the resin, I'm going to touch on the basics of what is polyethylene. So to start off, polyethylene is really just made of ethylene monomer units. So ethylene monomer is this molecule in the upper right-hand corner here of your screen. Just 2 carbons and 4 hydrogens, very basic. Comes from ethane cracked to give that double bond. And when you polymerize those all together, you end up with a linear polyethylene molecule, which is this middle image over here on the right side. This polyethylene molecule can be modified a number of ways, which I'll go through. But one of the good things about it is it being a thermoplastic, you're able to heat it and melt it and then cool it and harden it several times over, which is very advantageous, obviously, for fusing, which will be covered later on. But that's one of the primary benefits of it being a thermoplastic. So the specifics of high density polyethylene sort of fall in, the density of it, hence the name. It's a pretty broad density range, actually. Technically, it goes from about a 0.940 to a 0.970 density. Realistically, polyethylene pipe that's used, the P4710s, are going to be closer to a 0.949, 950. And the range that's allowed by the standards for a P4710 is 0.947 to a 0.955. So what is the resin?
Why do we care about density? Why does a customer care about density?
Yeah, so I will get into that a little bit later in more detail, but density is really going to define the pressure handling capability of the material. As the density increases, typically the pressure handling capability is going to increase as well. And so the higher you can go in density without compromising your crack resistance, the higher hydrostatic design stress you'll be able to get, which is directly related to your pressure handling.
Thank you.
And so what does the resin supplier control with the materials we're making? So there's a few different things. First is molecular weight. So molecular weight is going to be defined as how many ethylene monomers make up that chain. The more ethylene monomers you have in there, the higher the molecular weight. The other is molecular weight distribution. That's the range of the size of the chains within your polymer. The broader the distribution, the larger the difference between the biggest chain and the smallest chain. That has an impact on processability of the material. And then the last is density. And that's really going to be an indication of how tightly the chains can pack together. You can imagine for that middle image, a linear polyethylene is going to be able to stack very nicely together and create a very ordered structure. When you add a co-monomer in, though, which is what we're able to do, you get these little side branches, which can be seen in the lower right-hand image. These little side branches, as you might imagine, make it more difficult for the chains to pack together neatly and drop the density. But those side chains are actually very, very important for your slow crack growth resistance. And that's what that SCG stands for in the bottom bullet there. A slow crack growth resistance is going to dictate your service life of your pipe, and the density is going to dictate the pressure handling capability. So now I'm going to speak to briefly the pipe performance as it's gone over the years. So one of the things you can see here is as time has gone on and the PE classes have increased, the pressure resistance has also increased. And it's really a function of density. So if you look in the bottom graph, the furthest left bar, it's a low density polyethylene P1404. And then as you go further to the right, you see that first digit increasing from a 1, 2, 3 to a 4. And that first digit is going to represent the density range that's associated with that specific resin. And as you increase density, which is what's happening as that digit increases, your hydrostatic design stress on the y-axis also increases. And that's going to dictate your pressure resistance as well. So what else has been done over the years? You know, why didn't we just start with a high density polyethylene? Some of that goes into, again, what I mentioned earlier, the slow crack growth resistance. So on the left-hand side here, we have a unimodal and a bimodal molecular weight distribution. The unimodal molecular weight distribution is dictated by a single peak, as seen on the top left, and a bimodal is dictated by the double peaks. And really what you're getting with the double peaks, and speaks to the highly engineered part of the resin, is you're able to tailor what exactly you're doing. So on the right-hand side, we sort of have a breakdown of these double peaks. And the left side, where you see this dash peak, that represents a low molecular weight homopolymer. And so what that gives you, the low molecular weight increases processability, so that it helps with the extrusion rates. And the homopolymer helps with your stiffness. The right-hand side is where you put all of your co-monomer to increase your short chain branching, which is very important for your slow crack growth resistance. And then you're also making a very high molecular weight material to give good impact toughness and also to help with the slow crack growth resistance to well. High molecular weight helps with the slow crack growth resistance. And what you end up doing is you create a balance of properties to give not only good density to increase your pressure handling capability, but also give good co-monomer incorporation to help your slow crack growth resistance. And that's why the bimodal distribution has been huge for the industry in being able to increase the pressure handling capability. And
hold on one second. Dan Landy, we got a couple people had trouble getting in. I sent you their emails. Would you mind helping them? Thank you, Mike.
No problem. No problem at all. And so this graph here does a good job, or this page here does a good job of better illustrating unimodal versus the bimodal advantage. So for example, here you have 3 plots: pipe service life versus slow crack growth resistance, slow crack growth resistance versus density, and then hydrostatic design stress versus density in the bottom. So if you want a high pipe service life, all right, so you go high pipe service life in the middle plot, and then you want a good slow crack growth resistance. If you go over to the next plot, good slow crack growth resistance for a unimodal resin leads to a lower density. And at a lower density, you're naturally going to have a lower hydrostatic design stress. And vice versa. If you want to increase the density, you move up the line on the hydrostatic design stress. This gives you lower slow crack growth resistance, and it gives you lower pipe service life. So what bimodal ends up doing for us is it shifts that middle plot, that plot in the middle right. It shifts it for us. And so then what it allows us to do is have a higher density while still getting good slow crack growth resistance compared to the unimodal resin. So if we go to the bottom again, as you can just follow the green lines, higher density with a bimodal to give a higher hydrostatic design stress. At that shifted line gives us better slow crack growth resistance, which in turn gives us higher pipe service life. So these are some of the advancements that we've been making in the resin industry to improve the capability of the high density polyethylene pipe resins. And it's
particularly important, Mike, to this audience, because these advancements are directly responsible for our ability to make large diameter, high pressure pipe.
Exactly. Yes, it's a very good point. Exactly. So as we increase the pressure handling capability, it allows more pipe size capability to be able to come out in the market. And polyethylene pipe resins, they have some other benefits. It's a good balance of stiffness and flexibility, which is good if there's an area of high seismic activity, and even during installation to be able to move things, bend things to get it into the ground. Really good chemical and corrosion resistance. It's a tough abrasion resistant material. Good impact resistance, and obviously being thermoplastic is fusible, which is a huge advantage for the material that'll be covered later. Now, the advantages or the advancements that I had mentioned about going from unimodal to bimodal, there's a ton of other advancements that have gone on, but two of the other large ones that have really benefited the extra large pipe is chlorine resistance and slag and slump. So what is sag or slump in pipe production? So this really does a good job of illustrating it. On the left-hand side, you have, I would call it a desirable pipe. It's very concentric, not ovalized. The wall thickness is uniform around the circumference of the pipe. However, with a standard quote unquote P4710 resin, as you get really large in pipe diameter and your wall thicknesses increase, when it's sitting there in the molten state, gravity can work on it. And that material can slowly flow to the bottom of the pipe, as seen in that right-hand image. And that's an issue. The standards have only so much that can allow for variation in the wall thickness around the pipe. It's also not cost effective because you're having to account for put more material in there to account for that slumping that happens. And then from a handling perspective, it causes issues as well. So that can be a real issue, not only in the processing, but in the handling side of things. And this image on the right does a good job of showing what it looks like in the real world. You can clearly see on the bottom there how excessive it is in thickness compared to the top. And so what the industry did is they developed a quote unquote a low sag PE 4710 resin. It looks very, very similar to the standard 4710s. The only difference is it is able to resist that sagging or that slumping caused by gravity on the pipe. You can get up to about 3 inches with standard, and then with low sag resins, you can get up to we've seen greater than 6-inch wall thickness on pipes made, which is huge.
Yeah, pretty exciting. Great job. I'm hopeful that you'll stay around on the bench. Mike asked to respond to some questions. That would be really helpful. Great job. I find that very informative. And, normally to the audience, we don't normally go into that level of detail on resin, but the resin is just so incredibly important to your understanding of, why now polyethylene in the larger diameters for these incredible applications. Well, it's because the resin has advanced. So that's why we're doing it this way. Now I welcome Stephen Boros and Matt Danish. Guys, let's talk to you about specifically taking some of that resin that Mike produces at Lyondell and other companies, and what you guys do with it. Matt and Stephen, come on. Stephen, you want to take the next couple of slides?
Yeah, I'm good with it.
Take it away.
I need you to start my camera.
Or not.
So let me say, well, we'll get the camera going here in a minute, I'm sure. Thanks, Peter. Appreciate you having me on. So yeah, the resin is what we use as our vehicle to make the pipe. And converting that pipe into resin is no easy task, especially when you get into these larger sizes, heavier walls. Everything becomes a little more difficult. But that's what makes polyethylene great, is because we've been able to expand the size range over the years. Not just the size range, 54-inch, 63-inch has been available for quite a while, but in thinner walls. Now we're able to go to these heavier wall pipes to get up to the pressure class ratings and working pressure ratings that can very easily work in these raw water transmission systems that we're seeing them being used now. It's really quite exciting to see everything that's come along with it. Are you hearing me all right, Peter?
Yes, you're all set.
Okay, great. So one of the things we see on this, as you showed in this slide here, is the durability of the material and the ductility of the material. The toughness is what I like to call those two factors combined together of polyethylene, is what really gives it its ability to perform in these rigorous and difficult environments. So you can see multiple millions of pressure cycles, and these aren't just like partial working pressure ratings. This is the full pressure class of the system. and the surge over that working class or pressure class rating. So it's really unique in the world of thermoplastic or any type of piping system to have that toughness that it can withstand these type of cyclic and surge events.
Well,
So
Stephen,
with that,
you know,
you can get
in
up
my
to
view,
2 times. I'm sorry, Peter, go ahead.
excuse me, in my view, other than the ability to fuse polyethylene pipe, the biggest differentiator is we don't suffer from cyclic fatigue like PVC does. I mean, that to me, if I were an engineer, I would say, wow, what a difference. First of all, how can you be a pipe and not suffer from fatigue? But man, what a difference.
That's huge. You're right. I mean, and that's really a game changer that a lot of people don't fully understand how to take advantage of that. And that's one of the benefits of that polyethylene brings to the table. You know, these tens of millions of cycles is dozens of cycles every day for 50 years or 100 years even. So, like I said, making the pipe is the kind of the art and the science involved in this. Everything gets bigger. So the extruders have to get bigger, the dies become bigger, the tanks become bigger. So with all this though, comes the advanced uses of polyethylene. So you got to know how to handle it. You can't just pick up a piece of pipe as easy as you could before. So let's say, for instance, you know, one stick of 65-inch polyethylene pipe can weigh 18,000 pounds just by itself. So you have to have proper equipment to make sure you can handle that properly. And we've been working with these, you know, so all these are recognized within the standards today as well. So if you start all the way back at PPI with the hydrostatic stress board, and their listings of the materials, as Michael talked about earlier, you see some of the low sag materials in there that are good for these large diameter or low sag type applications, 4, 5, 6-inch wall. The standards have all been revised, AWWA C906 and F714, to readily take advantage of these larger sizes. So they're all in there with dimensions and capabilities and performance requirements all the way up to 65-inch now. So you can see the wall thicknesses as they change over time. Like I said, having, you know, up to 54-inch pipe, we've been doing that for, I don't know, probably 20, 25 years now in North America, but probably in the DR32.5, maybe DR26, DR21. But you can see when you start getting into these thicker wall pipes, you want to get into a PC 125 with a DR17, now you're talking 65-inch with almost a 4-inch wall thickness. So that's the minimum wall. So, you know, the average wall is going to be a little bit heavier than that. And even today, even though this table stops at DR13.5 for 54-inch, we can manufacture that today for these higher pressure classes. You know,
thank you for that, Stephen.
Yeah.
You know, go ahead.
No, I was just going to talk about this
Go ahead,
slide a little
Stephen.
bit.
Okay.
So the Water Research Foundation, it's an interesting thing. So it really depends on what your point of view is, or your frame of view as to what you call large diameter pipe. So the Water Research Foundation, and when they were looking at their water main applications, they defined large diameter pipe as 16-inch and larger. Today, as you see on the slide here, really 48-inch and larger is what we're calling large diameter, because 24-inch to 36-inch, 42-inch is really becoming very common these days. You can get it multiple places. You have all the fittings that go with it. You have the joining capability. You have the fusion machines that go with it. And just the all-around knowledge of how to utilize it and install it correctly and efficiently is, like I said, it's very readily available today.
Yeah, it's really exciting. And that's why we're seeing these projects that we're going to talk about today, Stephen. Good job. Thank you very much for that. And, you know, a couple of years ago during COVID, Stephen, our definition was 36 inches. But today we have so much good documentation about projects in the larger diameters that today it's 48 inches. And many people argue that that's even too small and that we really ought to start at 54 and 64. Anyway, so why are we here? Why are we talking about large diameter with HDPE pipe? And, you know, it used to be that the most innovative utility in the United States was in the city of Philadelphia. They had their own cast iron plants. They initially imported cast iron from France. Then they had their own plants here in the United States. Now they're a laggard. They really only use metal pipe. They have over 2,000 water main breaks a year. Their water loss rate exceeds 40%. They have embarrassing water main breaks that flood parts of downtown every year. So they're what we call a laggard in the industry. We also consider in our industry leaks to be a failure mechanism and failure of us, Stephen, to do our job
Right.
if we leak. So we spend a lot of time talking about failure and leaks, don't we?
Yeah, we do, Peter, because not everybody identifies it the same way. In some cases, a leak is not considered a failure, and I've never quite understood that. If a pipeline that's supposed to convey a fluid leaks that fluid out into the environment, in my mind, that's a failure at some level. And
Yeah.
with polyethylene, we call that a failure, not a leak, not acceptable.
Yeah, and as my friend Alan Ambler likes to say, we learn more from failure than we do success. I was out on this project in Arizona earlier this year with Mike James, and the contractor had put the poly right next to the reinforced concrete, and this line had been abandoned, Stephen, by Tucson Water for over 20 years. And now with slip lining technology, wow, we slip lined it with polyethylene. So there's a lot of great opportunities that we have with polyethylene. But Stephen, the key differentiator with this is absolutely the ability to fuse the pipe. You guys, can you hear that or not?
Yeah, it stopped though on my end.
But you can hear that? So Stephen, that is a 48-inch. That was a 48-inch butt fusion. And that process of clean it, shave it, heat it, fuse it is the same at 4 inches as it is at 48 inches. And it's repeatable.
Absolutely.
And the machines like you see there on the right and the left, these are the machines that are doing the fusions. And that same leak-free process that we show in our road shows, we talk about all the time, can be done even at the 3-meter diameter level.
Absolutely. Yeah, the equipment and know-how is readily available today.
So Matt Danish, I'd like to bring you on now. And if you could tell us a little bit about that fusion machine on the left that is incredibly fusing, it looks like almost 3-meter pipe.
Yeah, it's actually 3.26 meters, which is about 10.5 feet in diameter. And that was at a job site in the Middle East, welding together HDPE pipes for an intake system, for a water cooling system. And so you can, that pipe wall thickness is about, it was SDR 26, so it's around 4 inches in wall thickness, and definitely can be fused together with a typical butt fusion machine. This is just a little bit larger than you would normally see a butt fusion machine, but it works exactly the same way as your small little 8-inch or 12-inch machine that you could basically just carry around with your hands. So the principle's all the same. As you clean up the pipe, cut it, check it for squareness, apply your heater plate, heat, and then fuse it together. It's exactly the same principles as you would on a smaller unit.
Yeah, so Matt, tell us briefly, what do you do and who do you work for?
Agro American, I'm the technical manager for pipe and fittings for large diameter pipe.
All right, so you are the guys that are making the really large stuff down in South Carolina.
Yeah, up to 10.5 feet in diameter with almost 6-inch wall thickness.
Yeah,
and we also make the fittings to go with it. We'll have elbows, saddles, flange adapters, most any other components that go along with the system as well.
Right, and this is a project you worked on with ISCO up in British Columbia. It's amazing to me. I mean, I'm not about to take one of these big fusion machines, Matt, on the road with me, but it's amazing that this clean it, shave it, heat it, fuse it process works the same on 4 inches as it does on 3.5 meter.
Right, it's basically the same process. So as you shave the pipes, and you go through the heating process of melting the material and fusing it together. It's the same process from small pipe to large pipe.
Yeah. Hey, Mike James, thank you, Matt. Mike James, could you come on and tell us a little bit about the Talon and this project up in Alaska?
Yeah. Hi, Peter. Can you hear me okay?
Hey, Mike. Yeah, we can hear you and you look good.
All
Mike
right.
James, VP with ISCO Industries.
Yeah, thanks for having me. This project that we're looking at on the screen right now is a job that we did in Alaska about 3 years ago, I believe. It was a penstock line feeding a pipeline, a penstock pipeline, basically, and it was in a really remote application in Alaska. Had some really steep inclines to it. Remote application, pipe was brought in, large diameter, and fused up. There was, I forget how many feet were on this job, but several miles of large diameter pipe on it.
Yeah, so that machine was made in Tulsa, Oklahoma, which is where my organization is based, and you guys were central to the success of that project. I notice you have a unique inspector there, Mike.
Yeah, the bear. Yeah, that's Alaska. There's lots of bears. He's doing the fusion quality. He was inexpensive. We didn't have to pay him a lot because there was no mob or demob for him. So
yeah, he didn't go on strike either, I bet.
no.
Mike, can you tell us a little bit about these fabricated fittings and what kind of role they play on these large diameter jobs?
Sure, like any pipeline system, you're going to need fittings of some sort, right? So Matt was just talking about flange adapters to connect your pipe system together, either with a valve or maybe you're connecting two dissimilar materials together. Elbows, of course, like you see in the picture on the left. We can take those elbows, we can flange them or spool them to a certain diameter. So when you're in the field, it's a lot easier to get in the trench and install it. And then you also have T's or reducing T's. Maybe you've got a pressure reducing valve or a blow off of some sort, or maybe it's just a lateral line connecting to a different pipeline. So we can manufacture all of those in-house and ship them out to the field, either as standard fittings or maybe spooled like you're seeing in some of these applications.
Yeah, that's pretty impressive. So Matt, you sent me these images. I don't have personal experience with them. Please tell us about them.
So these are specialty fittings that we manufacture, part of our large diameter pipe. And so we can do different types of combinations of elbows, welding elbows together to make the S curve like you would see on the right and we put flanges on there or without, so you can just plug and play when you get to the job site. And then we do flange pieces where we elongate them so then it can be used for a particular application. And so, yeah, there's just a number of things that we can do with elbows, and these are all butt fused together with the same process where you weld two pieces of pipe together. So it's the same process where you have plastic to plastic butt fused fittings without any type of other connection being made.
So I noticed in preparation for this presentation, Matt, that you and Mike James were telling me about the Steinecker job that we'll talk about. And the image on the right looks like the 15-degree bends. I've been saying for years that we don't need 11s and 22s because we just bend the pipe. Why did we have to make 15-degree bends? Why couldn't we just bend the pipe in the trench? Is that a thing with large diameter that you just don't do it as much?
Yeah, absolutely. You could still use HDPE and bend it if you have enough radius of curvature. So basically our standard allows 30 diameter bending radius. So that means that if you had your pipe and you induce a curve into it just by bending the pipe, you can bend it up to 30 times the diameter of the pipe as far as that radius of curvature.
Mm-hmm.
And as your temperature changes, though, and also your DR or your wall thickness, things like that affect that minimum bending radius. So there are some ways to get around using elbows. So if you have enough real estate to work with your pipeline, to bend the pipe, though, with these larger sizes and heavier wall thicknesses, it does take a lot of energy to do that. So you do have to make sure you have the equipment on the job site to be able to bend the pipe. We also have the ability to make smaller bends, like a 15-degree bend in coordination with just a natural bend of the pipe, which whenever you're using a fitting or a butt fused elbow, the standards require you to either do a 100 diameter bend or come off of that bend, that elbow 5 diameters before you
Mhm.
start bending the pipe. So basically what you would normally do for laying out a pipeline system is do a combination of both an elbow and then a natural bend of the pipe.
Yeah, makes
Just
sense.
because, yeah, just because you can't really get exactly, we don't have the ability to dial in and make a 11-degree elbow. What we strive for is a 15-degree increment. So we'll make a 15-degree elbow or a 30-degree elbow or 45-degree elbow,
Mhm.
and then just use the natural bending of the pipe to get the more precise curvature that you need for the trench that you're
Good.
going into.
So Matt, I think it's important to understand that small diameter is a lot different than big diameter in that your point precisely was it takes a lot of energy to move the pipe. These things weigh a lot per foot, you know, as much as 500 pounds a foot, right? Or even more.
Correct.
Yeah. So that would argue for that. Mike James, you have something to add?
I do, Peter. Yeah, I think, obviously we're talking about large diameter. So the thing that you can do with HDPE, you can actually bend it into a complete circle, right? If you have a big enough space, if I have a piece of 1-inch pipe, I can turn it into a hula hoop. We've all seen that. But if you have a 65-inch piece of pipe, you need a big radius. Now, I'll give you some firsthand experience, and I think we've talked about this job before. And for me, it was a real eye opener. The job we did down in Guatemala about a decade ago, when I physically was down with those guys, talking to them about bend radius and where they would need elbows and where they wouldn't. And we got about halfway through the job walk, and the owner of the project went, Mike, I can't believe we don't need this many elbows. I said, Rudolph, you're gonna need some elbows in some areas, but you're gonna eliminate a bunch. What he was used to was running steel pipe, and every change of degree, every angle change there was, whether it was vertical or horizontal, they had to put an elbow in. With our pipe, because it is flexible, you eliminate a bunch of elbows. You won't eliminate all of them, but you do eliminate a bunch of them. So it was really good firsthand experience for me.
Right. So Mike, as a distributor, what is the process for engineers to better understand the fabrication process? You know, typically, Mike, we say, oh yeah, you'll have it in 2 weeks, but you know, honestly, it could take 4 to 6 weeks to get, you know, the 14 elbows you need if they're super large diameter. What's the process look like?
Yeah, again, it's really project dependent and size dependent as well. There's a lot of fittings that we stock and we manufacture in 10 of our facilities across North America. When you get to large diameter, you're usually talking about more project specific opportunities. But what I'll tell engineers is, pull us in early and let us help you get through that process. And then we'll help you decide what you need for fittings. The earlier the better. So if they are large diameter, we actually need the feedstock that Matt or Steven would make for us, and then we would take it and put it in our fab shops, or in some cases Matt could manufacture them. But that process, it takes a while. So you're probably 4 to 6 weeks, maybe at best, sometimes maybe a little bit longer if it's a big project, but you just need enough time to get that organized. Usually it's not an issue because you have to order valves and ARVs and everything else, backing rings and all that stuff that takes a while anyways. So as long as you're ordering all that at the same time, you're in good shape.
Matt Danish, I was pretty excited about this one. Why so many flanges? And here we're talking about polyethylene infusion, yet you've got all these flanges. Tell us about it.
Right. So basically what you have there on the right those are some elbows, 45-degree elbows. And really the flanges, actually the actual flange portion is all HDPE. It's the backing ring. That's a metal backing ring that you can bolt these together. And this was done just because, you minimize the amount of welding on the job site where you just plug and play, where you just basically bolt all the fittings together. So there's no need for doing welding on the job site. And yeah, it's amazing. I wish there was a person standing in here so you could get the idea how large this is, because this is what we call 3260 pipe, which is 10.5 feet in diameter. And then if a person was standing there, they would probably come up to like the middle line of where that cross is in the on the orange straps there on the end.
I do think it's important to reiterate what you said, Matt, about doing these kind of fusions on the job site. It's just not done, is it?
Well, we know we can do welding on the job site. It's just that the machine is so large, and it takes 6 containers to ship it with. So whenever it goes to a job site or truck, it's multiple pieces that it goes into. Then you have to do assembly on the job site. And then you have cranes that you need for both the operation and also for the installation. So it is cumbersome, but we can do a on site. So that's the reason why we also have the ability to then do just flange connections where it's just plug and play at the job site to minimize the welding.
Mike James.
Yeah, I'll just add a couple things. If Dan Landy was standing next to that fitting, yeah, it would look ginormous. But if Stephen Boros or myself were next to it, it's pretty ordinary. But
Of course, yeah, that's
there's the jab
constructive.
from him. The one thing I do want to mention too, when it comes to fusion welding, and we'll talk about this throughout this presentation, the fusion welding for HDPE pipe, although it does take a while, and it's mainly the cooling process that takes a while, you can fusion weld large diameter pipe way faster than you can steel pipe. And we're getting 2 to 4, maybe even 6 welds a day on a Talon fusion machine. A steel pipe is going to get maybe 1, and they're going to have multiple people working on that pipeline at the same time. So our fusion process, while it's not super fast, it's way faster than steel pipe.
So, Mike, we like to talk about our failure rates being the lowest in the industry, in the pipeline industry, but we do have failures from time to time. Tell us a little bit about what that process is and what are some of these mechanical repair options that are available to us.
Yeah, I mean, every pipeline is going to potentially have a failure, and sometimes it's just caused by external equipment or somebody grabbing with a backhoe or something happening to it. We promote 0 leaks, and I think if you do the fusion process correctly, you're going to have 0 leaks, but you still can have a leak for some odd reason. So what you're seeing on the screen here are mechanical fittings, mechanical repair couplings and repair fittings that are really primarily the same type of fitting that you would put on PVC or steel pipe or any other pipelines that are out there. They might be slightly designed a little different for HDPE to help restrain them and so forth. But all the common manufacturers that make those same repair couplings are going to make them for HDPE.
Yeah, good. And ISCO gets involved in that process from time to time. And we appreciate that advice. We have a new member of the Alliance, Robar. They're making some specialty fittings that are really fantastic. And of course, we got the old standby with Kraus, now owned by Mueller, who are making up to, I think, 64-inch diameter now, Mike.
Yeah, I think all of those companies, both those companies have good capabilities, and there may be some lead time to some of those. So if there is a lead time, I mean, if you're trying to fix a leak in the field temporarily to put a Band-Aid on it, I mean, you would do it the same way you would any other pipeline, and then you would plan a proper repair and come back and either cut that section out or flange it or put mechanical fittings on that. Maybe the lead time might take you a little bit longer.
Mike, you mentioned earlier that you have these fabrication facilities all over the United States. We're getting into some real big structures these days, aren't we?
Yeah, we are. We've been making structures to support pipelines for a long time, and the pipe that Matt makes today, the large diameter, ultra large diameter pipe, and even Stephen as well, that we use that all the time for all kinds of different manway structures, leachate structures, place to put valves and things like that. So you're seeing some of that here. And some are pressure applications, and some are just gravity or non-pressure applications like you're seeing here. And a lot of those are either fusion welded or extrusion welded, but you're still getting a fully bonded system out of that.
So a fusion weld is strong or stronger than the pipe weld itself. How strong is an extrusion weld, Mike?
Yeah, we don't say that they will meet the same pressure rating as a butt fusion weld, but if you've got a low pressure application or a gravity application or maybe just a couple PSI, it'll hold up to that.
Got it. All right, and then finally on structures, one of our webinar attendees sent us that image on the left. Mike, we're doing a lot of outfalls these days.
Yeah, we do outfalls, intakes and outfalls all the time, and it's a great pipe for that because you're dealing with a lot of the times angles and going offshore. You're in usually corrosive environments, so outfalls really around the world with large diameter is really common. Large diameter HDPE pipe.
What about manholes?
Yeah, we do a lot of manholes as well, and you see those pictures on the right there. though, that's really large diameter. I think we had a question on the panel earlier too about maybe other pipes. I know we're talking about solid wall pressure pipe today, and that's really our primary focus. But there is profile wall HDPE pipe that gets up to even larger than what can be extruded today. And in some of those cases, we'll use that profile wall pipe to make structures like what you saw there.
Yeah, we also have bead trimming as an issue, and this machine that we're about to listen to is in the 36 to 64 inch diameter range. So you don't have to put a guy in the pipe to remove that bead. Let's listen in.
Hello, Sean.
Hey,
Can
good
you
brother.
hear that, Mike?
All right.
yes, good.
Welcome to the main
Got
stage.
it.
Thank you. So this is our mega large bead trimmer. This one in particular is the ML36. We have 4 different sizes: the ML24, the ML30, the ML36, and the ML54. It has a standard reach of 50 feet, but it is capable of going up to 500. and
So the
possibly even
36 and
more.
54 means the diameter pipe
Sorry,
it does?
yes.
Okay.
So between all 4 sizes, it has an ID range from 18 inches up to 52 inches.
So you're really covering
We're
the
covering
bulk
a lot. Yeah.
and you know, seriously, when you get up to 64 inch or 100 inch, you can send somebody in on a skateboard,
Oh yeah.
right? With a scuba outfit. Maybe OSHA won't let you do that, but you don't really need a machinery to do that.
No,
Okay.
not for those diameters.
Yeah.
But anyways, this particular machine, it also has an automatic adjustable cutting arm, so it will be able to compensate for any out-of-round pipe as well as any high-low spots between pipe ends and fittings. If you notice, there's a cutter here with 22 carbide inserts, and this will rotate at 2,000 RPMs.
Okay, so instead of running a blade through this 6 inch like we did here,
Yes.
So this is a pretty cool machine. I have to like that. It's got a camera on there. It's got those carbide cutting tips. So that's for the internal bead. And then on the external bead,
okay. So Sean
we
is
have
out
this
here with me. We're gonna,
demonstration. And this is a pneumatic tool. And let's take a look at that as well.
and you remember the camera's behind you, right?
Yeah.
So or you got to move the camera so that you can get in, so you can see it.
So
Okay,
we'll move on
so-
from that. All right. I just wanted you to be aware that those tools are available. They are safe and they do the job well. I'm not arguing necessarily for bead removal. I'm just saying sometimes we want to remove the bead and there's good reason to do it.
Can I add to that a little bit, Peter, if you don't mind, while
Please,
we're
Mike.
talking about that, if that's all right? We talked about low slump material earlier. Mike was talking about it in manufacturing pipe. It's really important that low slump material is used in large diameter today, because if you do make pipe that is out of round or slumping on the bottom, when you actually put one of those internal bead removing tools in, and I've seen this firsthand, it's not always going to get the bead out the correct way. So I think having properly round pipe extruded correctly, and if you do have to remove that internal bead, it's nice to have that. And those tools are fantastic. I've used them in several projects in South America and up here in the US, and it's a great way to get those beads out if you have a gravity sewer line.
Excellent. All right. All right, let's move into some cases now, close it out. We're going to talk about 7 different cases. 2 of them are in Utah. One of them is down in Peru. And these are some pretty exciting applications. And I think there'll be some lessons learned in there. So we'll start first with the North Davis Sewer Project. Whose project is this?
I'll take that one, Peter.
All right, Stephen,
Stephen.
take it away.
Yeah, so we were fortunate enough to be able to supply the pipe on this project and help out a little bit with the use of polyethylene. So it's a great story, you know, it has a great environmental aspect to it as well. So the North Davis Sewer District collect about 34 million gallons per day before discharging into the Great Salt Lake. But because of where it was discharging into, and because the Great Salt Lake is drying up, as you can see the picture between 1984 in 2016, you can see it's about half the size it used to be. So a lot of these bays and estuaries don't get the right mixture of salt and fresh water. And if they don't, they get a lot of environmental issues, a lot of algae blooms, and just bad stuff for the native animals and environment that live there. So they wanted to keep this water going into the Great Salt Lake because you don't want to remove 34 million gallons a day if you can help it. So they found a way to reroute it to another part of the lake by building this 6.25 mile effluent pipeline. So you can see it was kind of a difficult installation. It was going out this causeway to another bay in Great Salt Lake so it could get to the right mixture of salt and fresh water. Again, 33,000 feet, 63-inch polyethylene pipe with a DR26. They had to use stainless steel for any type of vents or anything like that, just because of the highly corrosive soils they had in this environment. In fact, they couldn't use steel pipe, even if they wanted to, because it just eats everything up right away. They had to put a couple of concrete structures in here. And as interesting as an anecdote, they had to use stainless steel rebar. I didn't even know they made stainless steel rebar. And they had to use stainless steel wire to wrap the rebar with. So they dropped some regular rebar wire out there, and by even just overnight, it had already corroded. So that's how bad this environment was. But for polyethylene, not an issue. So you can see that it saved a lot of money over the traditional materials. It was very poor structural stability along a large part of it because it's a man-made causeway. So it had a lot of boulders and riprap and things like that brought in there to build this thing with. But they were able to do it with the polyethylene just because of the way that it can resist all of these types of soil movements. You can see here loading the pipe was really unique as well. So we made a system where we could load 2 sticks of pipe, so 90 feet of pipe total on one truck, a 40-foot stick and a 50-foot stick. And by doing that, we were able to eliminate about 460 truck trips from our plant to the job site. And if you look at, the Green Freight Bill handbook on this, we eliminated about 180 metric tons of CO2 just in truck traffic alone that we took off the road. So they had to look at, where it might also float, and they had to put concrete structures over that, where they had to use the stainless steel rebar I talked to you about, and they had to keep the cover the same height. They couldn't change it because the Corps of Engineers would not let them change any aspect of the topographic layout of the system. And then we also had to have a few spooled pieces here, and I'll let Mike come on and talk about that. So these had to be manufactured off-site at one of ISCO's facilities.
Yeah, thanks, Stephen. So we've got a facility in Kingman, Arizona, is one of our large fabrication facilities. And what we do on a lot of these types of projects, again, like I said earlier, is we identify maybe where there's fittings needed. In this case, some reducing tees. I can't remember if those were for vents, Stephen, or ARVs or what they were, but what we'll try to do is like incorporate those into the fusion plan. And if we can help eliminate some fusions in the field, what we'll do is we'll end up spooling maybe some longer pieces. Sometimes we'll put flanges on them, or sometimes we'll just make it so it's easy to get in and out of the fusion machine for handling. So a lot of those can be done in our fab facilities.
Yeah, going on with that. So Whitaker was a contractor on this job, and talked with them several times on and off on the project because they had some interesting things going on. Like I said, they had a very narrow right of way they had to work with. And so what they did is they developed a skid system. So they took the whole fusion unit and all the supports and everything, put it on a big metal skid, and then they laid out the pipe and then just moved that skid from place to place. So they could get a long string of pipe before they lowered it into the ditch. So again, anyway, we really like the society aspect of this. You can see that the group was very proud of it, reduced carbon emissions, and also kept this precious resource going back into the Great Salt Lake where it's so badly needed.
Hey,
Well, Stephen, you
polyethylene
talk
was the
about
only material that could do it.
Stephen, you talk about the ESG side of it. Mike Camera from Lined Up a Cell early in this talk, when you're talking about resin, he talked about that we harvest ethane from the wellhead. The ESG message for us is also huge because we're taking gases, Stephen, that used to be flared off, and now we're converting it to polyethylene.
That's exactly right. Yeah, full circle. Yep.
Mike James.
Yeah, I just want to add, I think on this slide here, it's important. We talked about the fabricated fittings and the spooling. But I think what's really important too in the fusion process, and it talks about it in the second paragraph,
Yeah.
contractor was required to destructively test, a couple of joints in the first 1,000 feet, then 2 joints every 5,000 feet. I think the way that you can do that, and I think this is a great example of it, is if you are doing quality fusion testing to ASTM standards, that's important. You have a quality fusion machine that is working properly, a quality technician, all of that is extremely important. When you get into the field though, how do you verify that? So you verify it using the data logger, which records the whole fusion joint process, where it was done, who did it, time, temperature, pressure, all of that. You record it, but then you still want to make sure that those fusion joints are good. Well, you can destructively test that safely today by using the guided side bend testing tool. And if you do that in combination, you've got belts and suspenders, you can sleep at night and feel good that, hey, my fusion joints on that project are good. So I think it's
absolutely good points, Michael.
Good job, guys. Let's go a little further south here. Matt Danish, come on. I was excited to learn about this, Matt. I'd heard about this job, but you shared this one with me. This huge sewer line failed 6 years after the contractor put it in, and the city of Lima, Peru was like, what do we do? Well, you guys came in and saved the day, Matt.
Yeah, this was one of the projects where it was already installed. And what we did was we basically did a pipe inside of a pipe slip line with HDPE 63 inch. And the problem is that since we were on such a deadline and there was not a lot of space to even put a welding machine down in the hole. So what we did was we just used E-couplers and E-couplered the pipes together and slid them into the existing line that had failed.
Yeah, so that was electrofusion, right?
That's correct. So this process was because we couldn't get a welding machine down in the hole for the tight space that they had available. And so what was then elected to do was to use E-couplers, electrofusion couplers, to weld the sticks together as it kind of like a jack and bore. You weld and you basically jack and press it into the hole. And this was then accomplished with the welding with the electrofusion couplers. We were able to do this project.
Yeah, pretty exciting, and I'm sure citizens appreciated it. But kind of basically a jack and bore polyethylene in 16-foot segments, which is unique length for over 1,200 feet.
And yes, and exactly what Mike James said before, your quality of your pipe is so important when you get to larger size E-couplers. Your ovality, your diameters have to be very, very good in order for the E-coupler system to work properly. There are some things that you do to make this system work. But yes, if you follow procedures, you have the equipment necessary to do this, it can be quite successful in welding pipes together with the electrofusion couplers.
So Matt, I see this is orange pipe. That pipe that Mike James talked about up in Alaska was also orange. I've been talking about black pipe and how important it is, maybe gray with sewer, but what's up with the loud color?
The customer wanted the yellow color just because they wanted to make sure that if it was ever dug up in the future, or everyone would know what this line would be in the future, because they were so concerned about damage in the future for the pipeline.
Okay, so it's for visibility.
Correct.
Got it. All right. Alan Ambler.
Hey, Pete, good to let you know that we've had a fury of great questions come right in on us. And we're also maintaining a lot of people's attention. We've got 15 minutes left. You guys are doing great with slides and definitely very involved here. Love the fact that we got lots of good questions rolling in, and great webinar, guys. Keep going right to the end.
All right. Thank you, Alan. All right, Mike James, come on back. Tell us about this very cool project up in British Columbia where you guys helped put in an outfall line.
Yeah, this was actually the largest diameter HDPE pipe in all of North America, solid wall pressure pipe, I should say. 88-inch pipe for a wastewater outfall line up in BC, and I think you're going to be there soon, aren't you, Peter?
Yeah, I'll be there in 2 weeks for 2 different road shows.
Yeah, this is the job that we worked with Agro on, collectively shipped pipe to the west coast of Canada, and very successful project. This was a project, I think, that was actually designed, I know it was originally designed in steel because they didn't know they could get HDPE in the diameters that we can now. So as we've progressed as an industry, these types of projects are becoming more available for us.
Well, it's pretty interesting. You know, I don't really understand because I don't know the geography well enough, but why would you fuse something 120 kilometers away from where you install it?
Yeah, I think a lot of just is based on logistics. I mean, you need area to fuse the pipe, right? You need laydown areas to fuse the pipe and then get it offshore. So it's probably more just for logistics on where they can actually perform that work. And then you can float that pipe. It's done now around the world where they actually extrude and manufacture pipe in long lakes, and you can tow it all around the world, and it's being done now. I mean, that's the advantage of our pipe. And again, this was designed in steel, and anytime you're designing steel, there's probably engineers on here know, you usually have to cathodic protect it. Sometimes you have to wrap or protect it as well. And then what I found out in some district energy projects too, Peter, is if you put a steel pipeline in a lot of cases, you need water treatment facilities or plants to be able to treat that pipe so you don't have those corrosion issues. And with HDPE, you eliminate all of that.
Well, we're gonna show that video you produced, but I want to ask a question first of Matt and Mike James that one of the engineers who's followed us for several years asked, guys, how do you pressure test these large diameter pipes? I mean, we talk all the time about put a cap on it, bring it up to pressure, hold it for 3 hours. How do you do it with this big stuff? How do you know these fusions are okay other than those destructive tests?
Yeah, we talked about the actual fusion destructive testing, right? So you could do that. You can do that in the plant as you're making pipe material. You can do it in the field and do a field test. Matt, if you're on, you want to talk about field pressure testing and what you could.
Yeah, so there have been some projects for we had 2,000 millimeter pipe or the 78-inch pipe that we actually done field pressure test where they actually had enough water there to fill the pipeline and put it under test. But we also do so much internal testing of our pipe, and then we also do weld testing to ensure the integrity of the welds. So it can be done in the field. It's something that is a major undertaking to do a pressure test in the field, but it can be done. It has been done before. And we also do so much of the testing and the qualification of the pipe to ensure that you have a good solid system.
Got it. All right, thank you for that. Let's watch this video. I don't think we're going to watch all of it, but let's get a sense of this project.
To be honest, it's totally awesome to be a part of this job. It's one for the history book.
It's been textbook. It's gone really well.
This is a reality now. HDPE is getting bigger. It is getting used in much more applications than it was before. Only ISCO would have been able to do a project like this. I mean, ISCO had the people, the resources, the technology, the specializations, the qualifications to be able to support a project of this scale. And there was a lot of people that were involved that made this successful.
Well, you get the idea. And thank you, Mike, for producing that video. I think it's really instructive to see it in video. Now let's go to the Tolt pipeline. I'm personally excited about this project because I've been trying to assist the Seattle Public Utilities, SPU, for years in their journey into polyethylene. And they tried, Mike James, probably 4 or 5 residential rehabs with open cut polyethylene in some of the neighborhoods there in the north side of the city. But then they surprised me with this one, Mike. Tell us about the Tolt job.
Yeah, well, our good friend Drew Mueller was heavily involved in this one as well. This is a great one because there was a lot of seismic concerns with the Tolt project being in Seattle, and it's a redundant but a major water line that's really important for Seattle. So they were concerned with seismic activity. They were concerned about during the slip line process, that there were some bend radiuses they had to get to. Of course, it was going downhill as well. but it's a great example of where HDPE could be used for slip line. It was 54-inch pipe, I believe, is what we slip lined it with. It was about 2,400 feet and fused up into 3 different sections. And they used a fairly heavy wall. I forget the DR. I think it was 54-inch DR 17. So pretty heavy wall. It wasn't used for pressure. It was more used for strength, for pull strength, to be able to pull long lengths. So again, 3 long lengths, 54-inch DR 17, 2,400 feet total, right into the host pipe that was existing. So another great.
Yeah, and I think we used Performance Pipes
performance, yeah.
pipe there that you shipped up. Great project. Congratulations to SPU, Drew Mueller, and ISCO on that one. And this one, I was like, I kept, over the last year, Mike, I've heard ISCO guys talk about the Steinecker job. I couldn't even figure out how to spell Steinecker, let alone say the word. I mean, I just didn't know anything about it. But learning about this project, it's so fantastic because all we hear about, Mike, is how the West doesn't have any water, and we've got to stop the farmers from using it all. And I'm like, yeah, but you're losing so much to evaporation. Tell us about this one.
Yeah, it's both evaporation and seepage, and being in Tucson, Arizona, we know how important water is to us. I mean, our water, as we've talked about, comes from a long ways away, from the mountains of Colorado all the way down to Tucson. I'm at the very tail end of it, so it's extremely important. This job is in Utah, and being in the West, of course, water anywhere in the West is highly important. I don't think most people realize how many open canals we have in the West, but there's just a million of them. And now what's happening is we're able to enclose those canals with pipe, like these diameters we're seeing here at Steinecker, 78-inch, I believe. And you minimize the evaporation, you minimize seepage, and also in this case, they had some corrosive or hot soils as well. So if you're going to enclose that, do I want to enclose it in something that I have to wrap or protect or cathodically protect? Or should we just use HDPE and eliminate all of that with bug fuse joints? So this was a canal project, and it's one of many that we've done in the West. It's the largest diameter one that we've done so far.
So these are those 15-degree fittings that Matt Danish was talking about, Mike.
Correct. Yeah, and what you see is a few of those elbows in there, but you don't see, just with every change of direction, horizontally or vertically, you don't see a ton of them, right? So we've got a great bend radius, but yeah, you don't want to kink the pipe either. So
did you really need 2 of those big fusion machines out there?
Well, we have to. We have a fleet of a few of these. We've got a couple of these Talon machines, the McElroy machines, and then the blue one we have as well. But we used them in conjunction out there on that job. And one of them was the Talon was really more of a production machine to pipeline down and put the pipe in as it was going in the canal. And then the blue Techno-Dewey machine was more for field fabrication and assembly work there. So yeah, we had both just in case as well.
So the purpose of all that heavy machinery is to pick it all up at the same time and lay it in? Is that it?
Correct. Yeah, it's just what you would see, the same thing with a steel pipeline job or anything else, except you're able to use excavators in this case instead of heavy pipe booms, pipeline side booms that you'd see on a steel job. So our pipe is heavy. There's no doubt it's heavy, but it's not anywhere near what you would see with concrete pipe or steel pipe or anything else. So
right.
You do get away with some less equipment and maybe not as heavy duty as what you normally would need.
The last time we did a big webinar, Mike, we talked about that almond farm irrigation job in California. And the guy that you had on camera for that video said that they pipelined that with a crew of like 5 guys instead of 15.
Correct. Yeah. And, we always have one fusion operator, right? You might have a couple people assisting or helping, but that job was a great job. That was actually replacing an old steel pipeline, really not that old. It was like 10 or 15 years old and was leaking all over the place. And they replaced it with 54-inch diameter HDPE pipe. That was for an almond farm. If you don't know how much water almonds take, they take a lot of water to produce almonds and almond milk and everything else, but another good job. So these pictures from Steinecker are great because this project just wrapped up just a few months ago. So it's a fresh project for us.
All right, well, we're close to being finished here, and we're going to finish close to on time, like we usually try to do. And I've met Mike, your colleague Brian Fletcher, this week down in Florida to talk with the city of Fort Lauderdale. Several of them came to our event yesterday, and they didn't really have much experience, Mike, with polyethylene before the big pipeline failure into the intercoastal waterway. When at that time they hired Murphy and David Mancini and Sons to do that $50 million emergency 7-mile, 48 and 54-inch diameter polyethylene horizontal directional drill job to fix their failing systems. Now, polyethylene is the predominant pipe in their capital plan, Mike, because of their tremendous experience with this.
Kind of a hard way to find out all the advantages of HDPE. A tough situation. Had they used it in the first place, they probably wouldn't have been in that position. But we do that all the time. We have on this panel a bunch of infrastructure superheroes, I call them, because we are actually out there while we're doing a lot of new pipeline projects. We're solving a lot of problems with existing pipeline projects, and that Fort Lauderdale job made a lot of headline news, and not in a good way, but they had to quickly design and install this. I say quickly, it wasn't done that fast, but they had a major catastrophe on their hands, and they used HDPE to solve that.
Yeah, pretty exciting from our standpoint, where we were involved to help educate them. And then, your Brian Fletcher came in and worked with the contractor and the owner. The owner developed his knowledge, their knowledge with polyethylene kind of the hard way. But polyethylene, it doesn't leak. And what a great way to solve that problem, because nobody likes to see a sewage leak. So with 17 crossings, 2 different diameters, a 54 and a 48-inch, there was a lot of big pipe, Mike, being fused.
Yeah, and you show it on the slide here, 4 horizontal directional drills. I think that's one thing that I see in our industry. We are used every single day for directional drilling, whether it's conduit, gas pipe, sewer pipe, water pipe, big pipe. Our pipe is the predominant choice for horizontal directional drilling.
So, Mike, why does Mr. C have to clean the inside of the pipe when he's just fusing the outside? Why is that necessary?
Well, you're fusing the wall, the entire wall thickness of the pipe, and you want a clean environment. You want to eliminate any opportunity for contamination as you're heating up the wall thickness and making that fusion joint. So it's just best to have clean inside pipe and clean outside pipe. Just clean as you possibly can.
Well, that's for sure. And with this video, I'll just give you a sense of what it looks like to move 48-inch pipe in and outside of the fusion zone. This machine is so large that there's a stand for Mr. C to stand on, and there's an excavator pulling the pipe out. And now on the right-hand side, there'll be somebody else who's going to move the pipe in to the next fusion. Those pipe stands, Mike, are pretty critical, aren't they?
Yeah, while there's some heavy equipment in this, Peter, it's not steel pipe. You wouldn't be doing that with a piece of steel pipe, and you wouldn't have a pipe stand like that. One pipe stand with steel pipe. So we're still lightweight compared to other materials for sure. And the fact that they're 40 or sometimes even 50-foot joints, right? That helps eliminate fusion joints as well.
All right, great job, panelists. Mike James, Matt Danish, Stephen Boros from Pipeline Plastics. Sorry I didn't introduce you properly, Stephen. And Mike Camera from Lyondell. Great job today. And to our bench, boy, did you guys answer a lot of questions. Dan Landy, could you come on again and remind us how we're supposed to get our PDHs, please, and how we connect with you if we want help with a project?
Yeah, please fill out the survey. We'll be ending the webinar here in about a minute. First name, last name, and your state of registration. Please leave your state of registration to make things a whole heck of a lot easier. There will also be an opportunity to request any information based on what you heard today, any of the free resources we offer. And then last but not least, if you'd like to discuss a project or have any special design considerations that these panelists or myself can help you with, we are more than happy to deal with you here sometime this week.
Great. Hey, great job, everybody. I so appreciate all your effort today. Great job. We kept our audience all the way to the end. So long. See you on the road.
Thanks, Peter.